and come back to the same particle either this way or this way, but the configurations seem identical, right? So does it always mean that double exchange you come back to the original configuration or not? So to understand this, one can think of what happens to the relative coordinate. I can have the relative coordinate between these two particles. If I take them, if I take the relative coordinate as a function of time and take it to the other side, then what you can see is that for a single exchange, the relative coordinate makes exactly half a loop, right? If I'm taking a particle around another, the single exchange, the relative coordinate will make half a loop. On the other hand, if I bring it completely around, you can see in the second picture, I've taken the one particle completely around the other, right? I'm taking one particle and I'm taking it completely around the other. So for two exchanges, it makes a full loop. Now, if you think of what happens in 3 dimensions, this loop which you formed like this, I can take it off the plane and just take it away. And it's like after you've done 10 or 2 loops, it's like going back to the original configuration. You've made no change at all, right? Because you've exchanged it once, you've exchanged it back, but then this is the same, exactly the same configuration as before. But if you're on a plane, you can show that if you exchange it once and come around, then you can actually count. If I think of the relative coordinates and think of that point as fixed, you can count how many times you go around the origin. So the essential point I'm trying to make over here, which I've shown in these two figures, right? If I try to take on a plane, if I take one particle around another, I cannot shrink that coordinate to a 0 because it goes through the other particle. So the idea is that in 2 dimensions, this is what means that in 2 dimensions, I can have anyone statistics. Mathematically, the distinction is that if I can take a single point, an origin out, then in 2 dimensions, it makes the system multiply connected, right? Because in 2 dimensions, what happens is that on a plane, if I take a particle around another, then I can actually count how many times I've gone around the other. In 3 dimensions, it doesn't make sense because I can always move it away, right? It's just the relative positions is what matters, this way or you're this way. That's only 2 things that can happen. But on 2 dimensions, you can see that I can keep it like this. I can go around again. You can actually count the number of times you've gone one around the other. This counting is what allows you to say that you can have, because you can count the number of times you go around the origin, particles are actually classified in terms of something called the braid group and not the permutation group. So what is the braid group? Is the group of paths through configuration space. And easiest way of seeing what are these braid group is via pictures. Supposing I have 4 particles, then I can I can exchange particle 1 and 2 and 3 here. Then I can exchange particle 3 and 4 here. The original configuration and the original configuration and the final configuration are the same, but you can actually exchange particles, and the number of times you exchange can be counted, right? So you can exchange it here and so on. And what are called the generators of the braid group are just the sigma 1, sigma 2, and sigma 3. If you don't do anything, it's called, you have an identity. You can also have inverse because it matters in 2 dimensions. Whether you take particles like this is a different configuration from when you take it the other way around, right? Because they'll differ. You can actually see which way you can go around because you're on a plane. You cannot move off the plane. And you can have group multiplication. You can start with one. So what I want to mention over here is that this braid group is something like a group. If you've studied group theory, and it has group multiplication, Young-Baxter relations, and all that, all of which you can see just through pictures. So the important point to emphasize again is that for bosons or even fermions, once you've exchanged twice, then you can forget that you've exchanged at all. When you exchange once, you get a plus sign or a minus sign in the wave function. But after you've done it twice, you don't need to remember the entire history. Whereas for anyons, the entire history is important. You need to know how it has exchanged with each of the other particles in a many particle system. And this is the reason even a system, if you take a free anyons without any further interaction, it acts like an interacting system. It's not like a free system. You can solve free system of any bosons and fermions using your StatMech, right? You get the Fermi-Dirac statistics, Bose-Einstein statistics. But you can't get that for anyons because it's like as if these all these anyons are interacting with one another by a long range interaction because of this fact that the history is important. So this phase can lead to many new phases and phenomena, and that is not surprising because you know that even for bosons and fermions, it's the sign, the bosons, which gives rise to phenomena like Bose condensation, right? Maxwell's statistics doesn't give you all those things, right? You need to put in Bose-Einstein statistics to get these new phenomena. Similarly, for fermions, you have superfluidity, superconductivity, metals, insulators. All of it comes from the fact that you have fermions. In fact, in 2 dimensions, I also wanted to make this other point. It's not just identical particles. Even if particles were not identical, you had one particle of one kind and a particle of another kind, it actually, you can count number of times these particles go around each other. And this is something which is called mutual statistics. So now with this, let me come to what are called non-abelian anyons, because what is currently useful in quantum computation is a generalization of these anyon quasi-particles called non-abelian anyons. I guess people are familiar with the general idea of quasi-particles in condensed matter systems, right? That if you have interacting systems, then it's not that you can always describe the system in terms of what are called quasi-particles, which may not be the original electrons themselves. Sometimes they're dressed electrons called Landau quasi-particles. Sometimes they, like in superconductors, they are Cooper pairs. Similarly, you can get these anyonic quasi-particles in 2 dimensions. That's the point that I have to say. So the anyons which just acquire a phase are abelian, and they're basically one-dimensional representations of the braid group. And to have non-abelian anyons, you need higher dimensional representations of the braid group. And that can happen only when you have many particles, degenerate ground states, with the particles fixed at their positions. For instance, if you have a wave function, this is like you may be familiar with spinor wave functions with more quantum numbers attached to it, right? So if you have a wave function and under an exchange, it doesn't just go to a phase, but it goes to a unitary matrix times the wave function. Because the wave functions are written in terms of columns. That is true even for a spin half particle, right? You know that the wave functions are written in terms of columns. So it's like if the wave functions are written in terms of columns, it goes to a unitary matrix times the wave function under an exchange. This also was discussed as early as 1988 by Prof. So now we can, I can like to motivate the thing by asking, why do you have so much interest in anyons these days? The main reason is that it's supposed to be relevant in something called topological quantum computation. And this is something many of you are probably familiar with, that I mean, topological quantum computers in general uses qubits instead of bits, and instead of classical bits. And the qubits represent the state of a wave function. For instance, a spin half, which can be in a state up or a state down. And unlike classical bits, qubits can be in a state of superposition, which is written as alpha upspin plus beta downspin. Or if it's not spin or generally any other states, it's just generally written as alpha 0 plus beta 1. And this is what, because you have this kind of a quantum, because you can use this superposition, it allows for parallel processing of information and much faster processing for some kinds of problems. For non-abelian, the reason non-abelian anyons are relevant to this quantum computation is because this degenerate subspace of the uh, particles of these non-abelian anyons, which are distinct. You have many states with the same physical configuration of particles. The particles are at the same position, but they can have multiple states. I'll come to that in more detail. And that's the reason this ground state degeneracy means that I can write, just like I have spin up and spin down, I can have these states can also be written in terms of some 0 or 1, which forms a qubit. I will form a qubit from these anyons, non-abelian anyons. That's what I'm saying. So what we will do is then try to prepare the system in one ground state, exchange two of these non-abelian anyons by using some kind of unitary transformations of them. Those are the gates, and then you measure. So that's how you make a quantum computer. Yeah, it allows for a continuum. I mean, you can, when you make superpositions, and these superpositions can take you from one ground state to another ground state. So those are the kinds of processes that we will can happen using unitary transformations. Maybe I'll come to that in some detail. These are the quantum gates, and they're the building blocks for these quantum circuits. And the reason this is relevant is because it's a non-abelian anyon. This is also something I'll have to say. It allows for something called fault-tolerant quantum computation, which I'll come to. So let me start with an explicit model for anyons. That's the easiest way. I'll be using second quantized notation, which I hope is familiar to everybody. The Majorana modes, Majorana fermions were initially introduced as, you might know in high energy physics, as possible new elementary particles which can be their own antiparticles, such as candidate neutrinos or something like that. But that's not the way in which we're going to be using. We want to think of Majorana modes as quasi-particles in condensed matter systems. They're called Majorana, they're not elementary particles. They're not even fermions, but we will be calling them Majoranas. They're just Majorana modes. They behave as non-abelian anyons. So this was introduced by Kitaev in 2001. And the simplest model, what is called the Ising model for these Majorana modes, is this model where you have a chemical potential term for the fermions. These Cx and Cx dagger are the fermion creation and annihilation operators. And these are the hopping terms for the fermions. And this is something called a superconducting term, because you can see that it's both Cx and Cx plus 1. It is not one dagger or this thing. It's like a pairing term, what is called a pairing term. And essentially, the idea is that you can write, these are complex fermions, right? So these complex fermions can be written in terms of two real modes, the gamma, which I'm calling the gammas, gamma A and gamma B. At every position, X is the position of the particle, you can write the complex fermion in terms of two real particles. Any complex number can be written in terms of two real particle numbers. So I can write Cx and Cx dagger like that. And once I write it, you can check that these are the kind of commutations. If these are fermions, these are the kind of commutation relations satisfied by the gammas. It basically satisfies gamma dagger is gamma because it's real. So what I can do is think of every fermion on a site. This is a site of, and I'm splitting it into two, what I'm going to call Majorana modes, the gammas. And what I'm now going to do is change parameters in this model so that these Majoranas get separated. Because in any model, I can always do this. It doesn't mean anything. The Majoranas are not separated. What Kitaev did was he found a model where he could actually separate out these Majoranas and put them at two different parts. And that is what gave rise to these Majorana modes. For instance, if I just think of mu less than 0, huh? At some point, yeah, you're going to be taking a linear combination. You're going to be changing parameters in the theory so that you can. In terms of the original fermions, it's a many body state, a complicated many body state.
So the CX would be written as C gamma X plus some other I gamma X prime.
I'll come to that. I'll just show you what I'm going to say. Yeah. So yeah, in this limit, when I take mu is 0, t is equal to delta, I can show that this Hamiltonian, the same Hamiltonian, can be written in terms of the gammas very simply as this. It just includes gammas at the same point. Right? That's what I've drawn over here. Now I'm going to go to another limit where I'm changing the parameters of the theory. I'll put mu 0, t is equal to delta. Then what I find is that the Hamiltonian can be written in terms of hopping, in some sense, hopping of this is at site x and this is at site x plus 1. So this is the kind of hopping that is now being allowed. So this is a highly correlated state in terms of the original fermions, but I can define new fermions on nearest neighbor sites if I want. And what is important is that this particular Majorana and this particular Majorana are completely left out. And because they're left out, I can write a non-local fermion. That is, I can form a fermion from this one and this one. This is something I'm going to call a non-local fermion, written like this, right? And now the energy of this Hamiltonian, because this Hamiltonian doesn't even contain these particles, energy does not matter whether this particular the ground state now is doubly degenerate. Whether I have 0 or d dagger 1, which is d dagger 0, are both degenerate because the Hamiltonian doesn't depend on it, right? So I have a non-unique doubly degenerate ground state, and these two ground states are what is going to make my qubit, a non-local fermion. And because it is non-local, Hamiltonian has no dependence on the Majoranas, independent of whether the non-local fermion formed from them is occupied or not. Ground state is not unique, it's doubly degenerate. So in a sense, this was Kitaev's magic trick. He found the model which could fractionalize the fermion and put different parts of it at different ends, different ends of the wire. Right, so that they can now behave as independent particles. You can think of them as independently having their own life. So, right? And I showed this picture for a very simple range of, but there's actually an entire range of parameters. For mu is greater than 2t, you're in the normal phase. For mu is less than 2t, you're in this, what is called this topological phase with a doubly degenerate ground state and with these Majorana modes. So I showed for one point, but it's true for all these things. So this entire this thing. And now the question will be, where will we try to look for such?
Is that a unique fractionalization, or it could be done with like different combinations of?
In this model, it's a unique fractionalization. It goes, there are two modes which are exactly at the edge. They're exactly at the edge only for the parameters I showed. Otherwise, they decay. In this region, for instance, they decay into this thing, but they exactly like this, t plus gamma at one end plus gamma at one, right? So these two things are what I'm going to call the two independent Majoranas. This model, I mean, as we saw the model as such, now we want to look for some kind of a Hamiltonian which will mimic this to get a realistic model. In this model, I have not put spin of the fermions. And the superconductivity is, hence, the only way you can realize it in real life is that p-wave superconductors, where the superconductor couples the same spins. That's the reason that you need topological superconductors or p-wave superconductors to realize Majorana modes. And why are these end modes relevant for quantum computation? It's precisely what I said, that whether d dagger is 0 or d dagger is 1 doesn't matter, they degenerate. And this is what forms the qubit, right? And this model has two zero energy bound states at the two ends, which can be thought of as fractional pieces of the underlying non-local fermion. And it cannot be easily disturbed by disorder. Usually the spin qubits, the problem is that any stray magnetic field can flip the spin. So that doesn't happen here because it's non-local. You need the disturbance to come to disturb whether this fermion is occupied or not occupied. You need a kind of a long distance. Both have to be disturbed. So this turns out that's why the occupation or non-occupation forms a qubit which is highly stable. So now let's look at, assume that you can have these few Majoranas. If you have isolated Majoranas, then one can make composite anyons by fusing two anyons together into the vacuum. You bring them together, then they either form a vacuum or they form a single fermion state. Right? Both of them, as I said, are degenerate. Since the fusion outcome is not unique, that's the reason it's called a non-abelian anyon. And I can now braid, to use it for quantum computation, I will braid these anyons. If this is for instance braiding of anyons belonging to the same fermion, braiding of anyons belonging to other fermions. Let me be more explicit here. If I just had two Majoranas, then I can see what happens under the exchange of Majoranas belonging to the two. That means gamma 1 goes to gamma 1 prime, which is some phase times gamma 2. And U12 is the exchange operator. And then the phase of the other exchange, this I can always choose to be 1, that gamma 1 prime has gone to gamma 2. But then the phase of the other exchange operator gets fixed. The reason being, the product of gamma 1, gamma 2 is forced to remain unchanged because the what is called the ground state parity, value of d dagger d. If you have an isolated system, even with superconductivity, I can't change the what is called ground state parity because d dagger d is either 1 or 0. I can add a Cooper pair to it, but I cannot change its parity. So an isolated system with just two Majorana modes, you can't do very much with it. What you find is that since the number operator cannot change, I gamma 1, gamma 2 cannot change, so you can't really achieve braiding with this. But if you have a system with 4 Majoranas, then you can try to see that how it moves in the degenerate now ground state manifold with 4 Majoranas. Then you can have states. There are two fermions you can make from the 4 Majoranas. One is D1 and one is D2. And I can have either both of them unoccupied, one occupied, one unoccupied, and so on. In this case, what you can see, because the states of the system are just given like this, D1 dagger N1, D2 dagger N2. In this case, what you can see is that now operator U12, if I just exchange, then it will not give rise to any braiding because it's like the previous case. I always have to have this fixed. It is twice n minus 1. But on the other hand, if I can take one Majorana from one of the fermions and exchange it with the other, then I can move in this subspace. So this is what gives you unitary gates in the system, which can braid. So, I mean, these are the kinds of things which are being basically used. You can create a particle in the 0, 1, 2, 0, 3, 4, and then you can braid them, and then at the end of the system, you actually have particles like this. So you can actually move systems through. So this is the idea of why it can perform unitary operations, which will be useful for quantum computation. So this you can't do. I mean, you'll have to take T gates. If you want to exchange two Majoranas in 1D, I'll have to put more gates like this, right? I'll have to take one like this, then bring it like this, then bring it like this. So people have formed what are called T gates to exchange Majoranas, 1D Majoranas, right? So that's something which can be done, but it's not strictly 1D. You need more. You have to take a wire like this and a wire like this. Take the Majorana from this end to this end, then move it here, and that's really a cheap exchange. But if you could form 2D, if you can have samples with 2D Majoranas, then of course it will be nice. Right now, even the 1D is hard to find, as the next thing I'll be talking about. Yeah. So this is what Kitaev and Preskill showed, that essentially using non-abelian anyons, qubits formed from the non-occupation of this non-local fermion and quantum gates. Majoranas are just one simple kind of anyons. There are many other non-abelian anyons, which can, including parafermions and even Fibonacci anyons, which can give many, many more gates, and that can lead to universal topological quantum computation. So yeah, as I already mentioned, different pieces of the fermion are at different locations. And so occupation of a state cannot be changed easily by local disorder. So the qubit is topologically stable. Stability will be proportional to the length of the wire that you have. And braiding is also something, it only depends on whether things are braided or not braided. It's not, doesn't depend on local properties. So you get topological protection from decoherence, noise, errors, and this is why it's called fault tolerant topological quantum computation. Now the real question. You have error correction here as well. I mean, one can do error correction in, you need less error corrections in topological quantum computation. In quantum computation, you can, of course, have error correction, Shor's algorithm, and so on, and many other ways of correcting this thing. For this, I mean, the errors, if you think of something like a toric code, right? The errors are like these anyons, and then you can correct them. But fault tolerant, you would expect that you'll need much less error correction. So yeah, you have the semiconductor nanowires. So the idea now is to look for a real system which mimics the Kitaev model. So that will be what people try to do. So the most promising platform is the semiconductor wires with strong spin orbit coupling. So essentially, for semiconductor wires, you have a plus and minus, you have both up and down spins. Now you put a spin orbit coupling that splits the up and down spins sideways. And then now when you put a magnetic field and then you put a chemical potential here, you essentially get something which has only equivalent of a single spin, because you want to mimic something with a single spin. And because these are not exactly opposite to one another, I can't do it here because then it will not couple to a superconductor. Here, because these two spins are not exactly opposite in the same direction, there is some component of it which is up and down. So I can also couple it to an S-wave superconductor, because in nature you only have S-wave superconductors. You don't have P-wave superconductors. So you're kind of forming a model which kind of mimics a single spin species with a P-wave superconductor. And this is the way it is done. If you find a semiconductor wire, proximatize it with a S-wave superconductor, this wire should have spin orbit coupling, and then you put it in a magnetic field. Then you get all the conditions so that this looks exactly like a Kitaev-like model. So by doing that, the idea is that you will get Majorana's at the two edges of this wire, because you mimic the Kitaev wire. There is when you have to choose your mu, v, u, all of these appropriately to be in the topological phase, and then you can make a.
So if I measure, let's say, the order parameters of the superconductor, it will give me S-wave.
It's an S-wave, normal S-wave. When it proximatized the superconductivity in this, which has been proximatized there, that acts like a P-wave. It's an S-wave superconductor. You can't.
So if I measure, I will just get
S-wave, standard S-wave superconductivity. So the theoretical proposal was that tunneling from the normal lead into the end of the wire should give you a signature of this gamma 1, which should be a state at zero energy. So this was the theoretical proposal in 2010. They expected a zero bias conductance of 2e squared by h. And many experiments tried to do it, including Anindya Das, who was from IIST. Right? He was at Weizmann at that time. So all of these people tried, they found it. But ultimately, those experiments all turned out to be wrong, because there were other explanations other than the Majorana. So quantized Majorana conductance, all of these articles were retracted. There was many articles which are not there. But now finally Majorana has been seen. In 2024, there's a paper. The title of it is Indium Arsenide Aluminium Hybrid Devices Passing the Topological Gap Protocol. Microsoft team with over 127 authors with 35 graduate students. And they've used a combination of local and non-local transport measurements, which now implies high probability of having actually detected a Majorana mode. They said that in roughly half of the 25 samples that they studied, it passes the cut. They've done all kinds of things to confirm that it is a Majorana, and they believe that they have the Majorana. But well, I mean, but they've been much more careful this time. They says passing the protocol indicates a high probability of detection of a topological phase hosting Majorana zero modes as determined by long physics. And this demonstration is a prerequisite for experiments involving fusion and breeding of Majorana zero modes. So I believe that Majoranas have been seen, but the jury is still out. But many of you might have seen this thing 2 weeks ago, where Microsoft unveiled something called Majorana 1, which is the world's first quantum processing unit, and they say it has 8 topological qubits, Majorana qubits in this. And they say that they intend to build a fault-tolerant quantum computer in years, not decades. So the thing is, I've seen whatever they put out, I mean, which is just basically a blog, and there's one paper, I think the papers are more careful, but the blog and all, they say very clearly that they believe that this will be done very quickly. So yeah, is this true or too good to be true? I don't know. Because if this really works, it's like, it'll be much better than all the qubits that other Google and all have been doing, because this is actually a fault tolerant quantum computer, right? If they can do it in some 10 years, 20 years, I don't know.
It is effective 8 or
Huh?
8, number 8.
Yeah.
Effectively 8 qubits or they have.
I don't know exact details. I don't know, but they're saying that they have 8 topological qubits, which means that they have Majorana qubits. They're claiming that these are Majorana qubits. 8 in number, right? 8 in number is what they're saying. And they're saying this quantum processor that they've built, in principle, can hold 1,000 topological qubits. So it's actually something that you can hold in your hand and you'll have 1,000 qubits. I don't know. So this is something to be.
So processor means they're able to break them.
I think they're saying that it's, but it's
more complicated than
actually this thing. I don't know how they, because they in the original papers they have not shown braiding and all. If you actually, they're saying that the processor, they actually can do the quantum unitary transformation which braids them. That's the claim.
they have done computations actually.
They have not done computations with this, but they're claiming braiding in this system. So we have to wait and see. It's very, very much too early to know what this is. So yeah. So in the last few minutes, I mean, this is what the main thing that I wanted to get across. I will just talk about a little bit about what about more exotic non-abelian anyons, parafermions, Fibonacci anyons, and so on. I mean, of course, that itself has just been seen, so these are much ahead in the future. So we don't know when they'll see. These are more exotic quasi-particles than Majoranas, and they cannot be realized like Majoranas in a free fermion model. The building blocks themselves need to be fractionally charged. And the motivation for why we would want to study more Majoranas is that even with the braiding of Majoranas, they don't lead to all topological gates. So yeah, even if they could do this thing, they will still need some non-topological gates to do some other operations with Majoranas. Whereas it's only with Fibonacci anyons you can engineer universal topological quantum computation. And these kinds of things can be constructed using quantum Hall platforms, but obviously these are all still in the range of theoretical proposals. And that's something I work on, so I just thought I'll mention it. Parafermion models are actually constructed by generalizing spin models. And it's like, instead of icing spins, if you have spins which can take 3 or more and so on, then you can construct models which have this, what are called shift and clock operators, which are again generalization of the icing model, but I won't go through this. So the essential idea is that the spins at a site are split and one has dangling parafermion modes at different edges. But where can such modes be found? What people found is that if you have fractional quantum Hall systems, then you can put a superconductor and an insulator on top of it. And in between that, you can measure, you can kind of create these, just like you could create Majorana modes at the edges of a wire, you can create Majorana modes at the edges between insulator and superconductor, proximatized with a quantum Hall system. So again, it's another way of mimicking the Kiraya model. And my recent work with Saurin from IIST Kolkata and his student, these are his students, and Kishore was a visiting student of mine at ICTS. So we've done some work on this. What happens to Majoranas, parafermions, and quantum Hall systems when there's edge reconstruction? And earlier we looked at spontaneous fractional Josephson current from parafermions. So I just wanted to, what is the question we tried to answer? We wanted to see, I mean, if you can create people, when you talk of quantum Hall systems, you know, there is also something called edge reconstruction in quantum Hall systems. These are again very technical, I'm just mentioning it. And these reconstruction is inevitable in realistic quantum Hall samples from semiconductors. Graphene one still doesn't know. And what we wanted to see is whether we can look for signals of Majoranas and parafermions in the Josephson effect that one gets from this. And just a reminder of the Josephson effect, you know that for a normal, so between two non-topological superconductors, you get a Josephson current which has a 2 pi periodicity, because it's like as if you can have 2e hopping between the two superconductors. On the other hand, people have also looked for something called the Majorana-Josephson effect, where if you have Majoranas, then between two at these edges, because you'll have superconductors, it's as if you have an electron hopping between them, and you'll get something called a 4 pi Josephson effect. And for parafermions, you can generalize that and you get something called the 12 pi Josephson effect. So these were things that we looked at in our work. And we also looked at what happens when you have edge reconstruction. And what you can see is that how does the Josephson effect behave because of this edge reconstruction. And by some detailed analysis, we showed that if you start with the nu is 1 system, the many body system still spectrum still has 4 pi periodicity. But the edge of the effect of the reconstruction leads to two distinct Majoranas, one from electrons and one created from 3 quasi-electrons. And the experimental signature is that the amplitudes of these Josephson current would be indifferent. So in general, okay, again, I don't think I really want to go through this. Main Majorana modes robust to edge reconstruction, our answer was yes. And that's all I'll say here. Because the experiments to do these things are not very done yet, right? And recent experiments have only so far shown coexistence of quantum Hall and superconductivity. More than that has not yet been shown. So there's a long wait for realization. And edge reconstruction in graphene is still very preliminary. To see Majoranas in this system will take considerably more effort. So I'll leave it at that. And I'd like to end my talk with mentioning that in March 2020, Preskill made a bet to be settled on March 1st, 2030 at midnight with somebody called Professor Dowling. And will someone have finally made a topological quantum computer? And Preskill said yes, Dowling said no. And the stake is only pizza and beer. But yeah, it looks to me now that maybe Preskill has a slight chance of winning. So let me, this is a... No, I think already quantum supremacy has been established, right? At least with Google's... Not with topological. Yeah, I don't know. Yeah.
Edge reconstruction is something to be, or
Huh?
is edge reconstruction what you were mentioning?
That's in 2D, in quantum Hall systems. It's in quantum Hall systems. Yeah. So yeah, I'll leave you with a poem which was written by Preskill in 2005. Because my aim here was to show you that non-abelian anyons are interesting from many points of view, theoretical as well as experimental and for applications. Thanks for coming to listen.
These anions, they are possible in two-dimensional systems.
Yeah.
But in reality, it's a three-dimensional world. And even if we make something very thin, is that the only thing required to have two-dimensional system?
Yeah, I mean now, of course, the fact that they have made these things, right? You do have quantum Hall samples which are effectively two-dimensional. They are in 3D, but the quantum mechanics are such that the lowest energy it is so deeply down that the third dimension doesn't make a difference, right? The quantum mechanical states are in the two dimension. So it's sufficient. Graphene is, of course, directly two-dimensional. It's a single layer. But even if you don't have a single layer system, as long as the wave functions are confined to the plane, and that they can do in many systems, you'll have anyons. So physically, that's no longer a constraint now.
Thank you.
You need your original variables to be fractional.
Original variables to be, yeah, already interacting variables. They can be spin models or they can be fractionally charged quasi-particles.
They need not be fractional.
They have to be, meaning they cannot be just electrons. They can be interacting electrons. They don't have to be fractional. You can have them in interacting systems. You can't write.
Sigma was both.
In the paraformulas and the which we were doing, it's mu is equal to 1/3 quantum Hall effect. So that way the particles were fractional. E/3 quasi-particles charged. I'm sorry, I went through that in an end because
Are there generalization of entire chain in two dimensions anions?
there's a Kitaev story code model, yeah, which has mutual. It doesn't have Majorana's, no. From 2D models which has Majorana's, physically no. But then you have these topological insulator models where they have vortices, and the zero modes connected to these vortices, and the topological insulators can also be in non-abelian anyons. They can be Majorana's. People have looked for Majorana's on that, but it hasn't been created.
You are mentioning about the fault-tolerant nature of topological quantum computer. Can you go into more details into that part?
Fault-tolerant?
Yeah.
No, what I meant was, I'm trying to see what what I meant here was that uh, because it's a topological phase of matter, right? Majoranas are found in a topological phase of matter where what you've done is actually you have to, in general, in any topological material, you know that it is drastically different from the normal state because it's the entire state of the system which has to change. I mean, if it's a large system, then it's not that you can't make local changes, meaning in small parts of the system that will not change the whole system, right? So here, let me think of this. The case I was thinking was a one-dimensional wire, right? Now, if it's a one-dimensional wire is in the normal phase, then you don't have any edge states, right? And then nothing can, it's in a non-normal phase. When you're in the topological phase, then you have these excitations which are fractional charge quasi-particles at two different ends, right? So if I just now make some kind of local changes to the system, I can't easily transform it to a normal state. It will still be in the non-local state. And the way this braiding is done is by changing, like, yeah, here, right? I mean, it's like you're going from this 0 state to a 1 state or something like that, right? 0, 1, 2 has gone to a 1, 2 state. That required the entire system has completely changed now, right? What I'm trying to say is that if I have some kind of disorder or something like this, some noise or disorder at this end, it can't change whether this state of the system without also changing, it has to change both 1 and 2 simultaneously to change the state of the system, right? And these are, you have to assume that these distances are long enough that it's not local. When I think of a spin qubit, I'll be thinking of it at a single point, right? And then the spin qubit, if there is some kind of decoherence or noise or something, can easily flip. So it can change its state. Whereas the wave function that you write for this state cannot easily change. If I write something as alpha times 0 plus beta times 1, because to change from a 0 to a 1, this whole thing has to change. Right? That's what I mean.
Yes. As you told that Microsoft, after all these years, finally detected marijuana. So what are some typical challenges that occurs when we try to detect them?
When you try to
detect marijuanas.
When you try to detect marijuanas.
Yes, like.
Okay. In the reason the first few detection attempts failed, right? Many years ago when they were trying to first do these experiments, right? The reason it failed was because, firstly, there are many other reasons you can get a zero energy ground state, right? Some impurity state, something over there can also, you measure it. What they were measuring is a very simple, okay, how do I? Yeah, this. What they're trying to measure is that they're just taking a normal lead. They're putting, trying to see what is the current through this system, right? And to get this zero energy ground state, I don't have any of the graphs that they had. You can get it from there are a lot of things which mimic. There are Andrew Brown states, there are disorder oriented bound states, all of them can mimic it. To prove that you actually have a zero energy state itself was very difficult. What these people did was they could actually show this entire what they did was they could do experiments which could go from here to here. They could show regions where they did not have a Majorana mode, and by changing parameters, they could show the Majorana mode. They could show Majorana modes at both ends simultaneously. So these were all the checks that they did to make sure that what they've got is really a Majorana. One of the things which really people believed was the fact that you could actually tune through what this is called the topological phase transition. So they could tune through it and show the existence of the Majorana. But a lot of Microsoft's things, the experimental details are actually somewhat classified, right? They're a company. So even though they published, until some other group can also do it, right? I don't think it will be believed. I mean, you need to have many groups do it. And I think there are many technological difficulties in doing these experiments. It must be at very low temperatures, small sizes, small these things. Not allowing. I don't know. I mean, I should find out from the experiment.
Okay, maybe one more question.
Quantum domain. It's
quantum
domain, yeah. Meaning it's valid for quantum particles. But yeah. Now when we want something, means a computation chip or something, so it is coming out of the quantum domain. So I just want to know the meaning, quantum calculations, how we are
Well, I mean, that those details, I don't know how they put it on this processing chip, but yeah, all the experiments have to be done in the quantum domain, right? So
meaning when it is a physical thing that can be
that we
held in
hold,
hand,
yeah, I
so
don't
that
know. Can anybody
that
else
is
help me? I, yeah, because these all calculations are done in the quantum domain. Experiments also are mostly done in the quantum domain. But when they bring it out and you have something that you hold in your hand, I don't know what, how much processing, how they do it.
I suppose in a dilution refrigerator with
Yeah,
room temperature,
yeah,
bring it out at room temperature for you to see this.
yeah. But what do they mean by having a quantum processor chip? She's what?
Processor, whatever is made in
They,
the
but
is
they'll
made
actually do
away.
the experiments inside a in the quantum domain inside a dilution refrigerator, I
So they are
suppose.
at temperatures which are very low.
but
When they
it's for
really do the
temperature
experiments,
is
when they
not.
do this quantum computation, presumably they will have to have all the, uh,
Like if it is very low temperature and all this, we can't have it for mass publication. Sorry, mass.
I don't know. I think
In,
it's that people expect it to be there when they say that it will be a quantum
Slim
computer.
images, no, the big dilution images there Google shows.
Yeah, but ultimately they have to do it in tiny parts, right? But I suppose initially what is it called? Those vacuum tubes and all were also very huge. Then transistors came, no? Like that.
like
Maybe
that's
there'll be quantum things which will come. You people, I don't know.
Continue the discussion more properly because
Yeah.
we are pressed for time.
Okay.
So, leaders know